Hi folks, welcome to chapter 3. In this chapter, we are going to be looking at atomic particles. We are going to be looking at the properties of particles. We are going to be looking at the periodic table. We are going to be looking at ions, and then we will look at the oxidation states. Now, let's start with atoms. So, everything around us, the things that we see, the things that we touch, the things that we feel, the things that we smell, they are made up of matter, and matter is made up of atoms. So everything that is around us is made up of atoms. Now, let's see what is the origin of the word atoms. So in 400 BCE, there was a Greek philosopher called Democritus, and Democritus said, if you have anything and you divide it into two, you are going to have two halves. And if you continue dividing it, you will arrive at a point where you will not be able to divide it again. At that point, it is said to be indivisible. So in Greek, that word indivisible is atomos. So atomos means indivisible. So an atom is indivisible. So that is the origin of the word atom, from the Greek word atomos, which means indivisible. So an atom of an element is indivisible. Now, let's look at the law of conservation of mass. Between the years 1743 to 1794, there was a chemist called Antoine Lavoisier, and he proputed the law of conservation of mass, where he said, in a chemical reaction, matter is neither created nor destroyed. So, for example, if we have a reaction between hydrogen and oxygen, there is going to be that conservation. Now, in this example here, we have 4 grams of hydrogen, we have 32 grams of oxygen. So if we add all of these, we are going to have 36 grams of water. So nothing has been lost. So matter has not been destroyed, and nothing has been created. So that is called the law of conservation of mass, which states that in a chemical reaction, matter is neither created nor destroyed. Let's look at another example here of the law of conservation of mass. Now, if 16.0 grams of methane reacts with 64.0 grams of oxygen, 36.0 grams of water are produced. How many grams of carbon dioxide are produced in this reaction? So our reaction is between methane and oxygen. We have 16.0 grams of methane, and we have 64.0 grams of oxygen, and the product is carbon dioxide and water. So we have 36.0 grams of water. So how much of carbon dioxide is produced? For us to know the amount of carbon dioxide that is produced, we need to sum the masses of the reactants and see what we get. So the masses of the reactants must be equal to the masses of the product. So the mass of carbon dioxide is going to be 44.0 grams. Because if you add 44.0 grams to 36.0 grams, that is exactly going to give you the sum of the reactants. So there is that conservation of mass. Now, let's look at the origins of the atomic theory. So we are going to look at the work of John Dalton, and John Dalton postulated that elements are made up of tiny indivisible particles called atoms. Remember, Democritus said the word atomos, which means that they are indivisible. And Dalton also said the elements are made up of tiny indivisible particles called atoms. Dalton also said the atoms of each element are unique. So each atom of each element is different. So an element of copper, it has copper atoms. An element of gold, it has its own atoms. Atoms can join together in whole number ratios to form compounds. Take note, whole number ratios to form compounds. Now, atoms are unchanged in chemical reactions. So you cannot change atoms. You cannot be reacting carbon and oxygen and you may end up having sulfur. No, the atoms are unchanged. So, for example, if you are reacting carbon and oxygen, you are going to obtain carbon dioxide. So you are reacting one atom of carbon and two atoms of oxygen to give you carbon dioxide. Now, let's have an understanding of the atomic theory. We know that charcoal, which is mainly carbon, if you light charcoal, it's going to burn with oxygen to give us carbon dioxide. So charcoal is mainly made of carbon and it reacts with oxygen to form carbon dioxide. Now, let's look at the three foundational ideas of atoms. So the first one is that all matter is composed of atoms. The second is that the atoms of each element have unique characteristics and properties. And the third is that in chemical reactions, atoms are not changed, but they combine in whole number ratios to form compounds. Now, the question is, can we see atoms? In the past, it was said that atoms were invisible, but there were some scientists that were working with IBM, so they actually developed a method in which we could visualize atoms. So we can actually see atoms now. Now, how can we visualize the arrangement of atoms in a compound? For us to be able to visualize the arrangement of atoms in a compound, scientists use what is called X-ray crystallography. And X-ray crystallography shows us how every atom is connected to the other atom in that structure. Now, we've seen the atoms, and atoms have each element has unique atoms. Now, the elements that we have seen, the elements are classified in a periodic table. So a periodic table is a table that has an arrangement of elements, and the elements were arranged by Mendeleev, Dmitry Mendeleev. So he worked with a periodic table and he arranged elements in order of increasing atomic masses. So he also placed elements in the same group, which were some of the elements that had the same properties. For example, we are looking at halogens here. Halogens are the group 7A elements. So they were classified in the same group because they had similar properties. Now, here in the periodic table of elements, we have metals, which are the things that you see here. These are the metals. So these are metals that you see in blue. Metals. We have the non-metals. The non-metals are in light green or lemon green here. So everything here you see, these are the non-metals. So as you see here in this key, and everything in between here, these are the metalloids. So we have the metalloids. So here the actinides and the lanthanides, they actually fit in here. So you see the lanthanides, they continue from 57 up to 71, then you see 72 here. And the actinides, they continue from 89, you see from 89 here, you see 90, and up to 103, and here 104. We have just taken out the lanthanides and the actinides so that everything can neatly fit into the periodic table. Now, what is the meaning of periodic? For example, you use a periodic table every day. The calendar that you have, the calendar is arranged in such a way that the days are arranged like from Monday, Tuesday, Wednesday, Thursday, Friday. They are arranged in a week. So that is the week, and all the days, like all the Mondays, they have something in common. Like in this periodic arrangement here, you see the 1st, the 8th, the 15th. So all of those are Mondays. So they have the same day. So let's look at the groups and the periods. In the periodic table, we have groups and we have periods. How are the groups arranged? So these are groups. As you see, these are groups. Moving down, you see the groups. So these are groups, these are groups. And the periods, these are periods going across. So this is period 1, this is period 2, this is period 3, this is period 4, period 5, period 6, and period 7. And for the groups, we have the group 1A, the group 2A, the group 3A or the group 13. We have the group 4A or the group 14, the group 5A or 15, the group 6A or 16, group 7A or 17, and the group 8A. So we also have the transition metals here. They have their own naming system, which is the group 3A. This is the group 3B here. For the transition metals, we have 3B, 4B, 5B, 6B, 7B. So those are the groups and the periods in the periodic table. So every group has similar properties. All the elements in each group, they have similar properties. For example, the halogens, they have similar properties. So those are the periods and these are the groups. So we also have family names for all the groups. Now let's look at the abbreviations for the elements. An element is represented by a name and a symbol. For example, carbon is the name and the symbol is C. Hydrogen, the name and the symbol is H. Magnesium and the symbol is Mg. So most of the names, the symbols are the first letter of the names, and there are some elements like sodium that names are taken from the Latin names. So for example, sodium here, you see the symbol Na, which is taken from the Latin name natrium. You also have iron. The symbol for iron is Fe, which is taken from the Latin name ferrum. So there are some that the names are taken from the Latin names, and there are some that the symbols are just taken from the first or the first two letters of that element. Now let's look at the blocks of the elements in the periodic table. In the periodic table, we have basically the S block, the P block, and the transition elements. So we have here, this is the S block, because the last electrons enter the S subshell. So we have the P block here, because the last electrons they enter the P subshell. We have the transition elements here, and we have the inner transition elements. So these are the various blocks. We have the S, the P, and the transition elements and the inner transition elements. Now let's look at metals. In our key, when we started with the periodic table here, we said these are the metals here. So everything here in blue, kind of, so those are metals, and that is what we are looking at. So the metals, they lie to the left of the periodic table, and here are all the metals. Every other thing that is not a metal has been left out. So everything that you see here are metals. So there is one thing that I forgot to mention. The periodic table, there are 118 elements that have been discovered so far, and out of those 118 elements, 98 are naturally occurring, and the rest of them are artificial elements. So these are the metals that we have. So everything here are the metals, and we have the transition metals here. These are the transition metals, and these ones below are the inner, the lanthanides and the actinides. They are the inner transition elements. Now, for the transition metals, we are going to see they are used in construction, for example, iron, and most of them we call them the coinage metals because they are used for coins. We have copper, which is used. This is copper here. We have gold, so all of them. So we have copper, which is used in making the pipes, the cables, and all the others. We also have gold. This is gold, taken from the Latin name aurum, and we also have silver, taken from the Latin name argentum. So these are all the metals, and what we are looking at here, we are looking at the transition metals. Now, these are the lanthanides and the actinides, and they are called the inner transition metals. Now let's look at the non-metals. So the non-metals, they are located in the upper right side of the periodic table, and also the first element, the hydrogen, is also a non-metal. So here are all the non-metals that we have in the periodic table. And an example here, we look at sulfur, we look at bromine, and now let's look at what we call metalloids. Metalloids have properties in between metals and non-metals, and that is why they are called metalloids. They are located between the metals and the non-metals, and their properties are in between. So examples are boron, silicon, germanium. So those are metalloids. Now let's look at the groups in the periodic table. Like I said, the groups in the periodic table, they have their group names. For example, the group 1A elements, they are called the alkali metals. So all the elements in group 1, that is lithium, sodium, potassium, rubidium, cesium, and francium, the elements are called the alkali metals. So these are the elements: lithium, sodium, potassium. So those are the alkali metals, and they are very soft. Now they react violently with water. So let's look at the next group of the elements in the periodic table. We are looking at the group 2A, and the group 2A elements or metals, they are called the alkaline earth metals, and those are the elements here. They are beryllium, magnesium, calcium, strontium, barium, and radon. And these elements, as we can see them here, they are less reactive than the group 1A. So the most reactive metals in the periodic table are the group 1A, the alkali metals. So the group 2A alkaline earth metals, they are less reactive and they burn brightly. So the next group of elements in the periodic table, we are looking at the group 7A or the group 17, which are called the halogens. And the halogens, they are diatomic elements. So we have fluorine, we have chlorine, we have bromine, we have iodine. So we also have astatine. So these are called the halogens or the salt formers. So that is the group name for the halogens, and here they are with the atomic numbers. Now, the properties of these halogens is that they are diatomic molecules in the elemental form. Like I just wrote out, they're always attached with a 2. If you want to write fluorine, is always attached with a 2, chlorine with a 2, bromine 2, iodine 2. And they form many different compounds. So some of the compounds, some of the products that we use that they contain halogens are Clorox. The Clorox contains chlorine. So they are found in most of these substances that we use at home. Now let's move to the next group of elements. In this case, now we are looking at the group 8A or the group 18, which are the noble gases. And the noble gases, we have helium, neon, argon, krypton, xenon, and this group 8A, they are generally non-reactive. So they do not form compounds because they have the noble gas structure, and they are gases at room temperature. So let's look at how we can uncover the atomic structure. We have seen the atom, we have seen the elements. Now let's know what the structure of the atom is. How is the atom? So the atoms of each element are unique, as we already saw, and we said the atoms combine in whole number ratios to form compounds, and the atoms are not created or destroyed in chemical reactions. So atoms are made up of subatomic particles. And what are subatomic particles? These are particles that make up the atoms, and we are going to be looking at these particles. So let's start by looking at the mass. And the mass is given in units of atomic mass unit. And one atomic mass unit is equivalent to 1.66 times 10 to the minus 27 kilograms. And the hydrogen atom has a mass of 1 atomic mass unit. Now let's look at the charge. The particles are opposite. The particles that are oppositely charged, they attract each other, and the particles that have the same charge, they repel each other. Remember, like charges will repel while unlike charges will attract. So a positive and a negative charge, they will attract, while a negative and a negative will repel. Same as a positive and a positive, they will repel each other. Now there is a Volta Barry that was created in the year 1800, the year that changed chemistry. So Volta invented the electrochemical cell, and in the electrochemical cell there could be that movement of electrons. So this actually changed chemistry. So with the invention of the Volta battery, the electrochemical cell, there was that possibility of separating atoms in a molecule. So you could actually use the Volta battery and you separate the molecules of water. Okay, so that actually changed the face of chemistry by inventing the Volta cell. Now let's look at Mendeleev's periodic table. With Mendeleev's periodic table, there were spaces that were left in the periodic table, and with the invention of the Volta cell, the electricity that was used, within 1 year, most of the elements that were not discovered in Mendeleev's periodic table were discovered. Now let's look at how we can identify charged particles. So charged particles are identified using plates. Okay, so we have plates, a positive plate here and a negative plate, and we have a source of the particles. So when particles were discharged from the source, it was moving towards a target, and there were plates, the positive and the negative plate, which was positively charged and the other one was negatively charged. So when those particles were discharged, it was observed that the particles moved towards the positive plate, which means that the particles were negatively charged. Remember, we said unlike particles, they will attract, while like particles will repel. So if it was attracted towards the positive plate, it means that it was negative. So this led to the discovery of the subatomic particles. This was carried out by J.J. Thomson, and this led to the discovery of the electrons. So the electrons are a tiny negatively charged particle. So when J.J. Thomson discovered the electron, he said if there are negative charges in an atom and the atom is neutral, it therefore means that there are also positive charges. And now he came up with a plum pudding model, where in the plum pudding model, he looked at the electrons like the dressing in the plum pudding, and the positive charges were scattered all over the plum pudding. So he envisioned negative electrons spread throughout a positively charged material. But then this did not last for long, as we will see. Like Ernest Rutherford carried out an experiment and it was disproved that the plum pudding model was wrong. So this is the plum pudding, where these are like the electrons and there are also positive charges. So every other thing you see are like the positive charges. Now, what J.J. Thomson postulated didn't last for long. Why didn't it last for long? Because Ernest Rutherford was working with his students, where he used a gold foil. This is called the gold foil experiment. He used the gold foil and he was using alpha particles. So he used alpha particles from a source and they were passing through a gold foil. And what Ernest Rutherford observed was striking. He observed that some of the particles went through the gold foil undeflected, some of them were deflected, and some of them even bounced back, as you see here. So these ones were bounced back, some went through undeflected, and some were deflected. So what did Ernest Rutherford conclude? Ernest Rutherford came to a conclusion that the atom is mostly empty space with a dense nucleus at the center. Why did he give this conclusion? Because most of the alpha particles went through undeflected. It means that the atom is made up of largely empty space. But some of the alpha particles were deflected, which means that there is a dense nucleus, because alpha particles are positively charged. So if they were deflected, it means that there is a positive center that helped to deflect those alpha particles. But surprisingly, some of them were reflected, okay, which means that the nucleus is really dense. So those were the conclusions that Ernest Rutherford came up with, that the atom is made up of largely empty space, the nucleus is dense, there is a small dense nucleus. Now, you see, this is how the particles went through the largely empty space. There was no deflection, there was no reflection. So that is why the atom is made up of largely empty space. Now, you see there is a deflection, which means that there is a dense small nucleus. So you see here that these particles were being reflected, which means that the nucleus is really dense. So let's look at the model of the atom as we see it today. So today we know that the atom has a positive center, and in the positive center we have the neutrons and we have the protons. So here at the positive center we have the neutrons and the protons, and the electrons are found on orbits here. We call these orbitals. So the electrons are found on orbits, and the nucleus has the neutrons and the protons. So if you are asked the atomic model, the electrons are found out of the nucleus, and in the nucleus we have the neutrons, which are neutral, and we have the protons that are positively charged. The electrons are negatively charged and they are found outside the nucleus. So that is the demonstration here. Now, looking at the volume of an atom, it is said that the volume of an atom is like a soccer or a football field, and the nucleus is just like an insect in the football field. So that goes a long way to show you how small the nucleus is. And even though it is small, it is really dense. So let's look at the subatomic particles. So the subatomic particles are the protons, the neutrons, and the electrons. And the protons and the neutrons, they are found in the nucleus, and the electrons are found on the orbitals. So let's look at the mass and the charge of these subatomic particles. So let's start with the protons here. The protons have a charge of +1 and they have a mass of 1.0073. So let's look at the neutrons. The neutrons have a mass of 1.0087 and they are neutral, they are not charged. Okay. For the electrons have a charge of -1 and a mass of 0.0005. So here you see the electron cloud. This is where the electrons are found. And here the nucleus. In the nucleus we have our protons and the neutrons. So these are the subatomic particles as we know. The nucleus contains the neutrons and the protons, and the electron cloud contains the electrons. Now let's look at the atomic identity. How do we add a particular identity to an atom? So the number of protons determines the identity of the atom. Remember, we've said the protons and the neutrons are found in the nucleus of the atom. So the number of protons identifies the atom. So the number of protons, for example, for hydrogen is 1. So if you see 1 proton, that element is hydrogen, or that atom is hydrogen. If you have 2 protons, it's obvious that that atom is helium. If you have 3 protons, it is obvious that it is lithium. Okay, if you have 20 protons, it is obvious that it is calcium. So the number of protons identifies the atom. So for 4 protons, we are going to have beryllium, and so on. Now let's look at the atomic number and the mass number. For us to describe the atomic number and the mass number, we are going to be using the periodic table here. And right here, what you see here, these are called the atomic numbers. So this is the atomic mass. The atomic number is equal to the number of protons in an atom. Okay, so hydrogen is 1, the atomic number is 1. For lithium is 3, so the atomic number 3. So it has 3 protons. For potassium, number of protons 19, atomic number 19. Now, so the number of electrons is equal to the number of protons for a neutral atom. If we have an ion, the number of protons is not equal to the number of electrons. So for an atom that is neutral, the number of protons is equal to the number of electrons. Now let's look at the mass number, or the atomic mass. The mass number is the number of protons plus the number of neutrons. So that gives us the difference between the atomic number. The atomic number is the number of protons. The mass number is the number of protons plus the number of neutrons. Now let's look at what we call isotopes. What are isotopes? So isotopes are atoms of the same element with the same atomic number but different mass numbers. So they have the same number of protons but they have different number of neutrons. So the difference in the atomic mass is as a result of a difference in the number of neutrons. For example, here we have a protium, we have deuterium, and we have tritium. So these are all like isotopes. Okay, so these are isotopes here. For the first one here, it has no neutrons, that's hydrogen. So it has no neutron, that is called protium. For the second isotope here, it has 1 neutron, that is called deuterium. And for the third isotope here, it has 2 neutrons, and this is called tritium. So the isotopes are atoms of the same element with the same atomic number but different mass number as a result of the difference in the number of neutrons. So these are the 3 isotopes of hydrogen. Now let's look at how we can write atomic symbols. So we are looking at helium here. We have to write the atomic number and we have to write the atomic mass. So helium here has an atomic number and it has an atomic mass or mass number. So each element, as you see it on the periodic table, you will see the atomic number and you will see the mass number. So the atomic number is called P, and the mass number, we've said the mass number is the atomic number plus the number of neutrons. So the mass number is P plus N, where P stands for the protons and N stands for neutrons. So for helium, helium has 2 protons and 2 neutrons. So how are we going to write the atomic symbol? So we have He, 2 protons, and then since it has 2 neutrons, it means that the mass number is going to be 4, since the mass number is the sum of the protons and the neutrons. Exactly. So that is how you write out the atomic symbols. Now let's look at this example. An important isotope of uranium has 92 protons and 143 neutrons. Write the symbol with the atomic and mass numbers. So for uranium, it has 92 protons and it has 143 neutrons. So the symbol is U for uranium. And now if we have to write the number of protons, we have been told that we have 92 protons. So the protons are written at the bottom here beside at the left. So we have 92 protons and then we have 143 neutrons. So for us to write the mass number is the sum of the protons plus the number of neutrons. So we are going to add the protons and the neutrons to give us the mass number. So we are adding 92 plus 143, that gives us 235. So the mass number, as we are going to write on the symbol, is 235. So that is how we write out the atomic symbols. Alright, so here you see the mass number of uranium here to be 238.03 instead of the 235 that we've had. That is because the 238 here is the average atomic mass, which is the weighted mass of all the isotopes of uranium. So uranium has different isotopes, and the average atomic mass here is gotten from the isotopes, the different isotopes and their relative abundances. Now let's look at the average atomic mass as we just saw for uranium. What is the average atomic mass? The average atomic mass is the weighted average of the different isotopes of an element. For example, we are going to see carbon here. In the example ahead, we'll look at carbon. So here we see that if we have to calculate the average here, we have 4, 1, 2, 3, 4 here. 1, 2, 3, 4. If we have to calculate the average will be like at the center. So that is how to get the average. Now, if we have just 1 here, and we have, for B, we have just 1 here, we have like 1, 2, 3, 4, 5, 6, 7, 8, 9 here. We see that the average is going to be really close to what we have to this side. Okay, so the average is going to be very close to 2. So that is 1.9. So we are talking about the weighted average. Now, let's look at an example of a weighted average. So we have a large number of poker chips. 10% of the chips are $1 chips and 90% are $2 chips. What is the average value of the chips? So the average value is given by the value of the A times the fraction A plus the value of B times fraction B. So we are going to look at the average value of the chips, and we said for $1 we have just 10%, and 10% is the same like 10 divided by 100, which is 0.1. So we are going to have $1 times 0.10 plus $2 times 0.90. So that gives us the weighted average. So here we see that the weighted average is $1.9, which is very close to $2. So let's look at it in terms of atoms. Now let's look at carbon. We know that carbon has different isotopes. We are looking at mainly carbon-12 here and carbon-13. So carbon exists primarily as two isotopes, carbon-12, which has a mass of 12.000 atomic mass units and an abundance of 98.93. Carbon-13 has a mass of 13.0034 and an abundance of 1.07%. Now, what is the average atomic mass of carbon? Now I'm going to ask you this question. You can pause. Is the average atomic mass going to be close to 12 or close to be 13? You can pause and then you answer the question. Okay, so let's do the calculation. So the average mass of carbon, we are going to have the mass times the relative abundance. So for carbon-12, we have a mass of 12.000 atomic mass units times the relative abundance, which is 0.9893, plus the mass of carbon-13 times its relative abundance. We will see here that the answer is 12.01. So it is very close to 12 because the relative abundance of carbon-12 is 98% and the abundance of carbon-13 is just 1%. So let's look at the summary of atoms and the elements. We said the protons, they determine the identity of the atom. We also said the atomic number is the same as the number of protons. And we said the mass number is equal to the number of protons plus the number of neutrons. So you should be able to carry out calculations. For example, if you are given an element like, let me just say sodium 1123. So if you are given an element like sodium and you are asked how many protons does this element have, you should be able to state that it has 11 protons. How many electrons does this element have? It has 11 electrons because it is neutral. So the number of protons is equal to the number of electrons. Now, how many how many neutrons does this element have? This element, the number of neutrons, N, is equal to 23 minus 11. So that gives you 12. So that is how you calculate all the subatomic particles, the protons, the neutrons, and the electrons. So if you are given any identity and asked the number of protons, the neutrons, and the electrons, you should be able to do that calculation. Now, we said isotopes are atoms of the same element, which means that they have the same number of protons but different number of neutrons. So we indicated how to write the atomic symbol, and we said for the atomic symbol, here is the atomic number and here is the mass number. So the periodic table is the atomic number and the average atomic mass. So the periodic table has atoms or the elements that are arranged with the atomic numbers and the average atomic masses. For example, here we have this element and we have the average atomic mass, which is the weighted average, and we have the atomic number. Now let's have a preview of the electrons. So we said the electrons are found on the orbitals. they are not found in the nucleus. What we have in the nucleus, we have the neutrons and we have the protons. And we said the electrons were discovered by J.J. Thomson when he was using when he used two charges and he passed the electrons through those two charges, and the electrons were attracted towards a positive charge. Now, let's look at the history of the atom. We looked at the Dalton's atomic theory, and the year was 1808. And what were the key ideas of Dalton's atomic theory? Dalton postulated there were three main things. He said the atoms are indivisible particles. And looking at J.J. Thomson, he postulated the plum-pudding model, and that was in 1904, where he saw the electrons, and he said if there were electrons and the atom was neutral, it means that there were also protons. So he postulated that there were protons, and he said they were like in a plum-pudding model, and he said that the negative electrons are spread through a positive matrix. But this did not last for long, as Ernest Rutherford proved it wrong. So that was the plum-pudding model. Now, Ernest Rutherford and his students, they were carrying out an experiment using the gold foil and alpha particles, and they discovered that the atom was made up of largely empty space. The atom contains a nucleus that is very dense, and that it can reflect or it can deflect alpha particles. So the last one that we are looking at here, we are looking at the Dalton's theory, the third part, because in the second part they said the atoms are indivisible particles. Now, atoms are indivisible particles, and the negative electrons are spread through a matrix. Now let's look at the Niels Bohr's model. Niels Bohr in 1913, he postulated that electrons orbit the nucleus like planets orbit the sun. So he said the electrons actually go around the orbits here as this planets go around the sun. So that was actually not true. But what actually is true, which is what we look up to, is the quantum model. That was in 1920 that was postulated. So electrons behave both as particles and as waves. So that is called the dual nature of electrons. So let's look at ions now. We have looked at atoms. We have looked at elements. Now let's look at ions. What are ions? When atoms gain or lose electrons, they form what is called an ion. And we have two types of ions. We have cations and we have anions. When atoms lose electrons, they form cations that are positively charged. And when atoms gain electrons, they form anions which are negatively charged. So an ion is an atom or a group of atoms with an overall charge. That charge can either be positive or negative. Now, atoms gain or lose electrons to form ions. So an ion can be formed by an atom either losing an electron or gaining. So let's look at an example here, a lithium atom. A lithium atom has 3 protons and 3 electrons. So if the lithium atom, if it loses an electron, it has a charge of +1, because if a species gains an electron, it attains a negative charge. But if a species loses an electron, it attains a positive charge, and this is called a cation. So the lithium ion here is a cation. Now let's look at the fluorine atom. Fluorine atom is in group 7 or is in group 7A or group 17. So it has 7 electrons in its outermost shell. So it can gain an electron, and if it gains an electron, it attains an overall negative charge, and we call such an ion an anion. So let me go back to sodium, to lithium here. This is called a cation, the positive ion. So if you want to write the lithium ion, this is how you are going to write it. Okay, so for the anion, the fluorine, the anion is spelled A-N-I-O-N. So that is how you spell the anion. And if you were doing that for fluorine, it is going to be this way. So that is how you represent it. Now let's look at examples of ions. Sulfur is atomic number 16. So sulfur atoms commonly form sulfide ions, which have a charge of -2. How many electrons are in the electron cloud of a sulfide ion? So sulfur, the sulfur atom has 16 protons, okay, which means that it has 6 electrons in its outermost shell. So the 16 electrons, sulfide ion will be 16 protons, and it gains 2. So that gives us 18 electrons. So that is how we get the sulfide ion. For you to be able to know how many electrons an element is going to lose or is going to gain, you just need to look at the group of that element in the periodic table. Metals form ions by losing electrons, and non-metals form ions by gaining electrons. So sulfur is found in group 6 of the periodic table. So it is going to form an ion by gaining 2 electrons. Oxygen as well is found in group 6. So it's going to form an ion by gaining 2 electrons.